So good afternoon. My name is Krishna. Basically, this is the very initial result where I'm going to talk about impedance measurement sensors for environmental contaminant detection. And we have been funded by the National Institutes of Health in the United States. I'm with Georgia Institute of Technology, but we also have a startup which is trying to commercialize some of the research that we did at Georgia Tech. The chemist, the engine behind these sensors is Dr. Elena Bekyarova, who is at Carbon Solutions in California. And my students, Gautam, who also happens to be my son, a really good student. And, and Georgia Tech, Qian, who is an environmental science PhD student. So very briefly, I have 15 minutes to watch. Nanotechnology-based sensors, this audience doesn't need much introduction, a very quick summary. But what I'm going to focus today is I'm going to show you a slide which is very, very important. That's the personal healthcare need for this kind of sensors. And then go into the sensor design, fabrication, and some measurements and conclusions. So nanotechnology-based sensors, basically, these are nanomaterials which are increasingly used in different forms, like carbon dots and nanorods, thin films, and so on. They are functionalized to different, functionalized with polymers and some other materials on the surface to detect specific gases like ammonia, carbon monoxide, etc. And we are focusing on ozone. And there are many applications you can see here. One of the most researched is the hazardous gas detection for industry and Department of Defense uses, security uses. So our basic sensing material is single-wall carbon nanotubes, which are functionalized to ozone. And this is one of the very innovative sensors, one of the first ones in the field, which came out of MIT in 2006, 2008 timeframe. So basically, it's a very simple interdigitated pair of electrodes on silicon, but they were able to detect parts per trillion hazardous gas, which is a DMMP. DMMP is a precursor to serine. And what they did is they did electrophoresis to align the carbon nanotubes perpendicular to these electrodes, and that got excellent sensitivity. So this is one of the very first applications of how nanotubes can be used to design a capacitor. And this is our first cut at a nanotube-based sensor for ammonia. This is a simple chemi-resistor, very similar to what I showed you on the previous slide. So there are two figures here. One of them is the raw material, which is pure carbon nanotubes. And the other one is raw material functionalized with this PABS, to detect ammonia. And you can see that there is the detection is 100, it's 100 parts per million ammonia. So without functionalization, I get only 12% change in the response. But with functionalization, I get a much higher scale, 38%. And the response time is very fast. In this case, a few tens of seconds, 100 seconds, and it is repeatable and it is reversible, right? So when you remove the source of gas, it goes back to the baseline, and it works at room temperature. So what we did is we took that chemi-resistive film and we put it here across a patch resonator. So this is an RF kind of measurement. So we have a patch resonator connected to some network analyzer here to measure reflection coefficient. And at the end of the patch, we have a small stub with a gap, and we place this nanotube film across that gap. And here we got, this has been reported in 2011, and we also got a patent on this last year. So without the film, without the gas, you get this blue line. And after you expose it to 25 parts per million ammonia, you get a 300 megahertz shift to the left because the capacitance increases or impedance increases, the reactive impedance increases. But when you remove the source of gas, it goes back to the original frequency. There is some distortion which is expected in a material, but those are all like problems to be solved by more engineering. Now, I want to spend at least a minute on this. There's a very exciting conference currently going on. It just started today in Geneva. I'm on the mailing list of World Health Organization, so I just found it out today. So they are talking about air pollution and health. And they released they had a press release yesterday which said that 90% of the world's children breathe toxic air every day. And 600,000 deaths in 2016 in red, age less than 15. Okay, 600,000 deaths due to respiratory illnesses caused by particulate matter, which is 2.5 microns or less, right? So this is a very, very concerning figure. And not only that, what is we are in India, right? Let's look at India. 100,000 of these deaths are in India. That is 1/6. 1/6 of the world's children dying because of particulate matter exposure is in India. And maybe 1/3 is, other, other small fraction is in China. Okay, these are two big countries like Brazil. We are actually, these are all man-made problems. I mean, I can talk for an hour here, but I just want to make sure that you understand the severity of this. So why is National Institutes of Health in US or similar organizations anywhere in the world, why are they interested in this problem? It's exactly this, to solve this problem. So what they said is, this is a cartoon of, not cartoon, some stock images of respiratory patients, asthma patients using a nebulizer, a breathing machine, and so on. So what if we provide these patients with sensors that they can wear? And it can detect exposure around them. They don't have to rely on weather bulletins and all, which are inaccurate, which are media hype. What if we give them figures, so some data that they can act on for their disease? So that's what we are trying to do. So that's what Ysense is trying to develop, prototypes of these sensors to help asthma patients. I mean, there's more statistics there. So out of all this pollution, the biggest one is particulate matter, and next is ozone. So these are the two main pollutants which affect respiratory health. So what we are trying to do is, this is from UC Berkeley, what we are trying to do is to develop a sensor like that, like a wristwatch kind of sensor, which patients can wear, and they can detect different pollutants in various forms like alerts or bar charts, more classified data, and so on. So our technology, sensor film technology, is carbon nanotube based functionalized sensors. So we are planning on making an array of sensors to detect different contaminants. And the most serious ones are nitrogen dioxide. Ozone is not even in this. This is an old bar chart that we created. And PM, of course, we will not be using nanotubes. PM is a completely different kind of animal, and it requires different technology. So what I'm showing here is a nanotube-based sensors, which are functionalized to a particular chemical, but there are also sensors which are more specialized to other chemicals. So there is some cross sensitivity, right? So in some cases, the sensor response increases positively. In some cases, the sensor response increases negatively, and that is based on whether the material is accepting holes or accepting electrons. Because of the chemical reaction with the analyte. So we have this tailoring a particular material to a particular gas. We know that. And these are some of the advantages. Okay, low power consumption, ease of integration with electronic devices, mobile devices, and so on. And this is one of the first sensors that we have developed. It's a simple interdigitated capacitor, not very exciting. Anybody can do this. We get some 20 picofarad capacitance. And then what we are doing, which is the subject of today's presentation, is to use an on-chip impedance measurement technique to characterize this sensor. So we are using AD5933, which is an analog devices impedance converter. Very briefly, you can find this information on the analog devices website, but very quickly, it's a digital frequency synthesizer here, deriving 16 megahertz clock and then synthesizing it to some digital signal, and that is converted into by this DAC into analog signal at a frequency between 1 kilohertz and 100 or 200 kilohertz. And then it is conditioned, signal is conditioned, and it goes through the unknown impedance. So this is the transmitter side, it goes through the unknown impedance. And then you have a transimpedance operational amplifier, which converts the voltage into an impedance. And then further analog to digital conversion, and then a DFFT to read the bits and give you complex number, magnitude, and phase. So some details on the fabrication. I don't have much time to go through this. I don't really like to put a lot of thing on the slides, but because it's 15 minutes, I have to put this so at least you can read it. But basically, we are doing two functionalizations: platinum decorated nanoparticles, and then covalently modified ODA molecules. So this is a inorganic polymer, and these are platinum nanoparticles on the surface of the nanotubes. And we basically synthesize it in the form of an ink. So we make an ink from these nanoparticles. We put it in a solvent and make an ink, and then spray coat the electrodes. So this is the TEM image before platinum decoration. So the nanoparticles, these are metallic impurities in the nanotubes, the white ones. And after decoration of the surface with platinum molecules, you get these black dots. So platinum is very uniform, very well distributed in this image. So there's a good conductivity enhancement because of this. And we did the frequency like a distribution chart here, and you can see that the average size is about 2.3 nanometers. And this is the measurement setup. So we have an ozone pre-calibrated source, which gives you a fixed concentration. And we have this Teflon gas flow chamber, and the sensor is inside that, a single sensor. And then this is our impedance converter chip, and this is an Arduino platform. So we are not using any sophisticated equipment like even an oscilloscope. We are just doing all this using this very crude on-chip solution in the form of an analog devices impedance converter. And at the other end, the output of the chamber goes to ozone monitor, which is the EPA certified reference monitor for the level that we find here. So this is the gold standard against which the measured concentration in the gas chamber needs to be compared to. And this is one of the first results we had. We could detect so what I'm doing here is it's a platinum decorated nanotube sensor. So we are cycling the ozone level from 10 parts per billion to 90 parts per billion, but so 10, 30, 60, and 90. But before we introduce the subsequent concentration, we try to retract or dissolve the ozone. So there is a little bit of going back to the baseline 0 parts per billion. But this is the first measurement that we did. What we found out is that the desorption is very, very slow. It takes 2 hours, and we could not sit in the lab and do that. Later, we found a solution. We had to increase the temperature. Instead of room temperature, we had to increase it to 75 degrees centigrade, and then we could bring these times shorter. We could make it shorter. But you can see that the sensor is acting like typical carbon nanotube sensors. Good absorption, tending to dissolve to baseline, but we didn't go all the way. So that convinced us that the sensor is working. Then we made 2 different sensors. One is platinum and one is ODA. Unfortunately, I don't have time to go through the details, but I just want to say that this is the impedance magnitude and this is the impedance phase. You can see that one of the sensors, the platinum, responds well in magnitude, and the other sensor, that is ODA, responds well in phase. So this is a very good input to start the experiment, right? So So you have 2 degrees of freedom that you can control by making an array of these 2 sensors. One gives you good magnitude response, the other one gives you good phase response. So any cross sensitivity to different gases or humidity can be well controlled by this combining sensors and then doing data processing later. So this is, this theme is being circulated by many authors in this conference. So it's an emerging research trend to use multiple sensors and do some processing. Now you can also do calculation, right? Okay, this is an impedance, magnitude, and phase. What does it represent? It represents parallel RC circuit. R is because of the nanotubes, and C is because of the layout of the interdigitated electrodes. So you can see that one responds well in resistance, the other one responds well in capacitance. So the same effect. And what we did is we looked at the frequency effect. We did just one absorption cycle and one desorption cycle, room temperature. Okay, we didn't increase the temperature, so the desorption is very, very slow, but it's okay. We ran the experiment. And what we found is that at higher frequencies, the change in the response is smaller than at lower frequencies. At this point, we don't fully understand the physics of this, but we can, we can use frequency also potentially as a parameter. So this table summarizes the frequency effect. You can see that most of the sensitivities are higher at 1 kilohertz and the lowest at 200 kilohertz, whether it's a magnitude in the impedance or phase of the impedance or the equivalent resistance or capacitance. And this is the sensitivity calculation. So in summary, we have presented the initial results for platinum decorated and covalently modified ODA group functionalized single-wall carbon nanotube-based sensors. We used an analog devices chip for impedance measurement on board or on chip, eventually impedance measurement between 1 and 200 kilohertz. We found that some sensors respond well in magnitude and the others respond well in phase. So some kind of array would be a solution in the future. Room temperature operation was to slow response, but yesterday I presented a paper where we showed that 75 degrees heating we put a small heater next to the sensor and heat it 75 degrees. We could reduce the desorption time from 90 minutes to about 30 minutes. And so our goal is to detect very low concentration levels because these are the environmentally relevant concentration levels for personal exposure. For example, whether it's India or US or China, it is the same level. World Health Organization states that 75 parts per billion is the level of ozone permitted on humans. Okay, anything above that is potentially hazardous. So we are in that range. And the limit of detection, which we are very happy about, is 10 parts per billion. So this is compared to many other sensors which were presented in the conference. They are focusing more at the higher levels, maybe for industrial grade kind of sensors. But when it comes to Fitbit kind of sensors or personal health use, you want to detect low levels with more accuracy. So that's what we try to do. Thank you very much.